The Elements is a very important book, and if you don't know about it yet, it's a bit of a shame we need to mostly pass it by here. It's also sort of a weird book when you stop to think about it. The reason most of us might not realize this is that it has been so influential on mathematical writing and thought that we tend to just chalk it up to being mathematical, and not notice that it's a little bit strange. It's important for us to understand something of the basic structure and scope of the Elements and the proof-centric tradition that it inspired. First, this book is only about math, mostly limited to what one can make with circles and lines. It has always been read as if it has a lot to say about the objective universe that's out there, but the book itself is just about circles and lines, just about geometry, maybe a little bit of number theory. These days, we take the separation of disciplines or subjects as given, but it was really unusual back then to have a book that was about such an isolated subject. This is not the only severe facet of the Elements. The structure of the text is very spare. Euclid starts out with some very basic definitions and ground rules or assumptions, which he calls postulates and common notions. This introduction is followed by numbered propositions and their proofs. Each proposition is a claim to truth, like that the base angles in an isosceles triangle are equal to one another. And then in the proofs, we're limited to only using the already given assumptions and any previously proved propositions that come before that proposition. That's it. That's all the book is made out of. There's no goal setting, no characters, no discussion, no motivation, no bigger story being told. Just stuff you assume and stuff you prove. This way of building up a system of ideas by starting with a few basic assumptions and reasoning out from them is called the axiomatic method, and it's really stuck. In an axiomatic system, no claim is made for big T truth of any of the initial assumptions. These days, they're usually called axioms instead of postulates, nor is there any truth claimed about the propositions that are proved from them, other than that they follow from those assumptions. No implications are made for what the overall picture is, what this system can be used for, or anything else that would seem to touch the concrete world of stuff and work to be done in the world. The propositions are merely some of the possible truths within the system, and nothing within a work like the Elements tells a reader which might be of minor or major importance. By the way, these days we have lots of words for propositions. They all ultimately mean the same thing logically. Stuff you prove. Theorem is probably the most common word. Lemma usually refers to a smallish theorem that comes along the way to a bigger one. Corollary kind of means the opposite, a small theorem whose truth follows from one we've already proved. No one ever told me this when I was first studying math, and I was very confused about all the different words I would see in the books. So now that we know basically what kind of a book the Elements is, I want to give you a sense of why this kind of thing caught on. In the West, replacing almost any other form of mathematical exposition once the Europeans really got going. It's not just the strong reliance on logic. Making logical inferences from A to B on its own isn't unique or special. This happens all over the place. What's special here is the number and simplicity of the initial assumptions. This is one of the times that humans have discovered that you can create great diversity from a very small number of initial ingredients. Euclid, in his book, starts with very basic, almost always painfully obvious sounding things. So obvious it's hard to imagine they can do anything. But this appearance is deceiving. Euclid takes these obvious facts and runs far with them. The overall effect feels very powerful to anyone who's ever hoped to understand the universe despite its apparent infinite complexity. So much can come from so little. We can appreciate some of this by taking a quick look at those basic ingredients in the Elements. Here's a list of the common notions, the basic assumptions that are general in nature. Common notion 1. Things which equal the same thing also equal one another. Common notion 2. If equals are added to equals, then wholes are equal. Common notion 3. If equals are subtracted from equals, then the remainders are equal. Common notion 4. Things which coincide with one another equal one another. Common notion 5. The whole is greater than the part. Pretty simple, right? And maybe it sounds a little bit like what you're allowed to do to equations in algebra. Euclid also starts out with 5 postulates. The basic assumptions are specific to geometry. Postulate 1. To draw a straight line from any point to any point. Postulate 2, to produce a finite straight line continuously in a straight line. Postulate 3, to describe a circle with any center and radius. Postulate 4, that all right angles equal one another. Look how simple these are. Essentially, you're just saying that you're allowed to draw lines and circles. I mean, come on, number 4, if you're drafting axioms to build a universe out of, this has to look like a lost opportunity. Well, this all goes a little bit sideways when you get to number 5. Postulate 5. that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side which are the angles less than the two right angles. Okay. That's just maybe one of the ways that this book could have been a little bit better. In its place logically, we could simply write down rectangles exist, and we would get the same mathematical system. Now, let's look quickly at what these humble assumptions yield. It starts out a bit slow. Here are the first few propositions Euclid establishes following from his postulates and common notions. Proposition 1, to construct an equilateral triangle on a given finite straight line. Proposition 2, to place a straight line equal to a given straight line with one end at a given point. Proposition 3, to cut off from the greater of two given unequal straight lines a straight line equal to the less. Proposition 4, if two triangles have two sides equal to two sides respectively, and have the angles contained by the equal straight lines equal, then they also have the base angle equal to the base. The triangle equals the triangle, and the remaining angles equal the remaining angles respectively, namely those opposite the equal sides. Proposition 5, in an isosceles triangle, the angles at the base equal one another, and if the equal straight lines are produced further, then the angles under the base equal one another. So it goes on like this. And after 46 propositions, Euclid gets to this one. Proposition 47. In right-angled triangles, the square on the side opposite the right angle equals the sum of the squares on the sides containing the right angle. Let me go ahead and write that down in modern algebraic notation. We start with the right triangle, and we're going to use our ability to label things. This is A, this is B, this is C. And in that case, the square on one plus the square on the other equals the square on the side opposite the right angle. Not much room to draw a square there, no big deal though. The thing is, this is not an obvious fact. No matter how hard it's been rammed into your head from school, it's not clear from looking at it. It takes a real ingenuity and imagination to notice this, to be able to figure this out. Keep in mind too that in Euclid's geometry, there's no measurement and no symbolic algebra. Euclid's actual proof of this is not the easiest to follow of the hundreds of known proofs of this theorem, but it is so close to the ground. This fact lies only 46 steps from those simple assumptions made above, like that all right angles are equal to each other. It's the sense of economy and connectedness that time and time again over the last 2,400 years or so keeps blowing people's minds and making them want to try their hands at either authoring new axiomatic systems or using them to understand the universe. There's this satisfaction in not just knowing that something is true, but also knowing why. But being able to follow the turtles all the way down to something numbingly obvious like all right angles are equal. There's security in knowing that the knowledge you develop isn't just a bunch of disconnected facts, but they all fit together and hold together. In math that follows from Euclid, why is taken to be at least as important as what. The way that Euclid wrote math then is how mathematicians write textbooks and journal articles now. It's basically just a litany of definition, theorem, proof, definition, theorem, proof. When asked what the main activity of doing math is, mathematicians today typically reply that it's creating proofs, not solving equations. Equations may be solved along the way, but the principal activity that they are engaged in is proving things. When you meet a mathematician, this will likely be the first misconception about their work that they'll try to clear up for you. Proof, in fact, became so central in this world that it almost choked everything else out. For a long time, a chauvinism around the activity of proof was so strong that it made it hard for historians of math to recognize the mathematical advances of cultures where math had not been defined in this way. It also blinded many to some key facets of mathematical innovation even within this same tradition. This is starting to change, but some of the books we'll come across are obviously under the spell of this particular brand of hero worship. Strangely enough though, despite how into axiomatics the Western world was, algebra itself was not developed into an axiomatic system until the 1800s. In the next section, I want to go back and talk to you about this verb solve and its history and where it comes from and what it means for us. So stay tuned for the next section of Anatomy of Algebra.